Hello there and welcome to this course on Introduction to Deep Learning. My name is Valentine and I'll be your instructor for the next 2 hours. In this course, we are going to follow this structure. So we'll get started learning about the learning outcomes. Then after that, we'll get to learn about what is deep learning, learn about important concepts in relation to deep learning. Then later, learn why and when do we apply deep learning. After that, we'll get to go through a reading and a quiz, which is basically a, a document that we have curated that contains generally concepts in relation to deep learning. But at the same time, we'll have provided more in-depth content in relation to those concepts in this particular reading. So you'll get about 10 to 15 minutes to go through that reading. Additionally, we will also had this particular quiz, which you will be required to complete as part of that particular section. After that, we'll go into our practice work, and this will entail going through a notebook that will contain practical examples as well as challenges that you can work on in order to implement those concepts that you will have learned in relation to deep learning. So we will go through classification as well as a regression example using the Python programming language, taking you step by step on how to create what are called deep learning models, which would be actually be one particular deliverable that in many cases you might end up undertaking or might end up working on. So aside from the practice notebook that we'll have provided, there will also be a solution notebook that will contain just the solution to the examples that you'll have been given, to the challenges that you'll have been given in this practice notebook. We'll also provide that once we have finished this particular section. So this particular section for practice work, we'll go through now the next steps, which will generally entail going through a project that will, have curated again, that will give you an idea of how those concepts that you have learned are applicable in a real life scenario. So the ideas for you is to apply those deep learning concepts in a real world challenge. That way you are able to see how those concepts actually are applicable in real life. We also provide some guiding notebook to help you go through that challenge. So this guiding notebook will contain some curated code that covers concepts that are not necessarily covered in this course. But when it comes to now applying now deep learning concepts, the guiding notebook won't be filled in those sections. So you will be required to actually write your code in those sections. Lastly, we'll also provide a solution notebook to the project that will just give you a better idea of how you would have alternatively gone about the solution. So yeah, so that's it. Generally, that's what to expect by the end of today. Hopefully, you're prepared to take this exciting journey. So let's begin. So starting off by the end of today, we expected to have achieved these learning outcomes. So we should be able to recall the fundamental concepts of deep learning. We should be able to describe how deep learning models work. We should also be able to summarize the advantages as well as limitations of deep learning. And we should also be able to construct deep learning models to solve for problems. What is deep learning? So deep learning is generally a subset of machine learning that uses what are called neural networks to simulate human-like decision making. When it comes to building machine learning models, which are generally computer programs that learn from data and then later are able to automatically make reasonable predictions, whether in a situation where we are working with a classification problem where we are trying to predict categories, maybe whether it's going to rain or not, or whether a customer will churn or not, or in other situations where we are also trying to use still those same machine learning models to predict some numerical value, something like whether not something like maybe the price of a house. You would rely on such a machine learning model to be able to make such a prediction. But in such situations, when we are starting out to build machine learning models, we would normally work with what are called base models, or just basic machine learning algorithms to create machine learning models which would effectively help us be able to arrive at some reasonable predictions. However, in cases where we want to, we realize that we fall short of some sort of accuracy that we want to have achieved by the end of a project. Maybe you created a machine learning model that required you to have an accuracy of 90%, but the best machine learning model that you are able to create from the basic machine learning algorithms ends up giving you something like 70%. And when you perform model optimization techniques, you don't still end up getting the 90%, maybe you get 80%. In such a situation, then we can decide to use advanced machine learning algorithms to be able to create far much more accurate machine learning models. And that's where deep learning comes in. It uses what are called now neural networks to simulate now human-like decision making, and to be able to make those predictions that are far much more accurate. So generally, deep learning, it's a subset of machine learning that uses those neural networks. And broadly, deep learning again is still part of what is called artificial intelligence, which is just the development of computer systems that perform tasks typically requiring human intelligence, maybe learning from data, making decisions, and understanding natural language. We'll get to learn about what these neural networks are, which are just basically computer programs or models trained through learning from experience that's again simulate human-like decision making, and we normally use them to just make better predictions. The different types of deep learning that we'll get to come across. This workshop, which is an introductory course, majorly focuses on the supervised learning aspect of deep learning. However, it's important to take note that there are different types of deep learning, which could be supervised learning, where you train your model to use what is called a training data set that has a label, has a target. And on the other hand, there's unsupervised learning, where you you don't train a model, but the model tends to learn from the data that it has been given without having a training process happening. So that's usually unsupervised learning. On the other hand, there's semi-supervised learning that combines both supervised and unsupervised approaches. So why would we want to consider deep learning? We've already mentioned a bit about this. So there's the aspect of data size, which when we are working with large data sets, especially when you have lots of data sets to the point of what is referred to as big data, then you can opt to go for deep learning as opposed to the traditional machine learning approaches, which are much more suitable for smaller data sets. Again, when you also want to automate feature extraction and selection, so deep learning might come in handy. But if you were to go the traditional route of using the basic machine learning algorithms to create your machine learning models, you might need to perform manual feature engineering in order to achieve your metric of success. If you want to also, again, an advantage of deep learning is that you're able to capture intricate and nonlinear patterns in a data set. This means that if you have features or variables which are, in the case of supervised learning, which are not correlated, do not have a correlation with the label or target variable, then deep learning would be useful, because in such a situation, the relationships in your data set would be nonlinear. Again, if you also want to obtain state of the art results when it comes to just being able to make predictions, then you can opt for deep learning. And if you also want to use deep learning, you want to create machine learning possibly for handling images as well as even other types of maybe video data, etc., then deep learning can be quite useful in such situations. These are some of those traditional machine learning algorithms that we would tend to work with initially before later onwards resolving to working with deep learning. And we'll cover random forest, which will help us be able to, first of all, set a baseline of how we can be able to, of baseline of what we can later compare to the performance of a deep learning model. So in our practice work, we'll create a random forest machine learning model, check its performance, then later create a deep learning machine learning model, and then check the performance and compare it with random forest to just see the difference in the difference in performance for both types of models. How do deep learning models work? I mentioned earlier that they tend to use what are called neural networks, or to be much more specific, they use what are called artificial neural networks, which are just adaptive systems that learn by using interconnected nodes or neurons, which are normally structured in a layered format. And that format usually resembles a human brain. So those neural networks would learn from data, and you could train your machine learning model to be able to also learn from that data and be able later onwards to classify data and make the predictions that you want. And the term deep just refers to the number of what are called hidden layers. So in an artificial neural network, which much more looks like what you have here, this is actually an artificial neural network, and this is the structure, and you have the circles are what they represent are the neurons, and the term deep just describes how many layers you have in between the starting or the input layer and the ending or the output layer. So if you have more layers in between, then in such a situation, then that is termed as just generally hidden. All right. So just to even just understand a bit more about the structure of of artificial neural networks. So just to explain a bit, normally you would have an input layer and an output layer, which you see at the far end. And the input layer is usually that first layer of our neural network that consumes our data. And the output layer, on the other hand, would be that last layer of our neural network that would produce the desired outputs or outcome. Then at the very middle, so that's the hidden layers, you would have now what are called just stacked layers between now those input and output layers that we had mentioned earlier. And each of the hidden layers, just like the input layers, would contain just neurons. So you have a neuron, a neuron, a neuron, a neuron, etc. And they're usually what are called weights and biases between those neurons, which determine the values of the neurons. So each of the neurons, yes, they do have some sort of value. And that value, say, for instance, for the hidden layers would be based off what are called inputs and weights that are values, which of course would help you to determine those the values of those neurons. And those are usually derived from the previous layers neurons, as you can even just see from the arrows that are in between the layers. Again, one more thing to note is that each layer, so this is one layer, this is another layer, this is another layer, but within the hidden layer, each layer has what is called an activation function, which just helps to transform the inputs of those neurons. So they're usually inputs, and those would actually, which are just values from the previous layer, would determine the value of the neurons in the hidden layers, and the activation function would just ensure that the values that are the end result are transformed between some lower limit and upper limit, and there are different kinds of activation functions that you would get to come across. So generally, that is usually something that you would need to take note when it comes to just explaining how an artificial neural network works, again, in relation to deep learning models. You can have as many hidden layers as possible, but again, the more hidden layers that you have, the more complex your machine learning model or your deep learning model becomes. When it comes to implementation of or the creation of a deep learning model, we would normally still follow the same steps as we would when creating the base models or the base machine learning models, where of course we start with data importation, we explore data, we prepare data, then we perform data modeling, and under that we split our data set, we instantiate our model, then again we then define our input, hidden, and output layers. Then we compile our model, train it, evaluate our model. The only difference that you'll note between the previous approaches when it comes to when it pertains to creation of machine learning models is what is from C to the C and D steps. C and D would actually be different from the previous ones, as opposed to if you wanted to create something like a logistic regression model, we would just instantiate our model, then we would train it, then we evaluate how it performed based on the training data. I think that's just it about how it works. But now, just to recap a few things, deep learning use cases are quite many, but some of the most known are image and video analysis. So we are able to automatically extract complex features from images and videos, and this allows us to be able to create machine learning models that effectively satisfy the metric of success that we had set initially. We're also able to apply deep learning models in situations where we are working with textual data that's in natural language processing. We'll be able to capture intricate linguistic patterns. We can also be able to apply, again, deep learning in medical diagnostics, where we are looking at ensuring that we make as little mistakes as possible when it comes to making predictions, because in such situations, those are actually high-stakes situations, which might mean whether a patient might recover or not. So such situations would require such kinds of tools. Again, in also autonomous systems where we are working with self-driving cars and autonomous drones, there's a lot of data being collected, and in such situations, then we can decide to work with deep learning. So those are just a few use cases. There could be many more that would be applicable. Why do we apply deep learning? Just for recap, why is it important? Just deep learning helps to address the shortcomings of traditional machine learning algorithms, which may not be able to effectively handle, help us be able to build machine learning models, which would be able to help handle high dimensional data. So where you have a data set with large numbers of variables. In some situations, also, why deep learning is important is that, again, it focuses on the right features during training, and it also helps us achieve higher accuracies. Lastly, when do we apply deep learning techniques? There's supposed to be deep learning. Sorry for that. Deep learning. We would apply deep learning techniques when we are working with large and complex data. So if we have large data sets, could be image, video, audio, text data, then deep learning works really well. When we are working with unstructured data, we could also end up doing the same thing, working with deep learning models. Still, unstructured data would be just texts, again, speech and image data. And also when working with healthcare and medical imaging projects, which are high-stake projects, even in manufacturing, deep learning would be really important in such situations. All right, so at this particular point, we are going to now shift to our reading. So you'll be required to go through this particular reading that we've shared. It will just provide just some more information in relation to what we have covered in that introductory bit. And then once you have gone through this reading, go through this quiz to assess your understanding. And then once you're done, we'll continue to go through to go into now our practice work. All right, so the next thing that we're going to do is to go through the practice notebook, which we have provided. If you are accessing this course from just different platforms, this might already be provided, but if you're accessing it maybe from YouTube or some other platform, you would need to become a member in order to access some of these resources. But we've also provided a sample notebook that just gives you access to the examples that we'll go through, but we haven't provided for the challenges. So getting started with the practice notebook, the first thing that we would need to do is to save this notebook as a copy so that we're able to make changes to it. And if we want to come back to it, we can always do that. So go to File, then save a copy in Drive to do that. And that should open a new tab. And you should have access to now a copy that you can work with. And then you can close just the original copy, which is the practice notebook that you see on your screen. Once we do that, we need to connect our notebook to Google servers. Just click on connect on the far end. This notebook, which resides on Google Drive, or just allow us to be able to execute. So once we have connected, we should be able to execute code in this notebook. All right, once you have done that, the next thing that we need to do is to import the prerequisites. So these are libraries that we need for working with deep learning. So in this section, you will find a few. However, there are a few more that we will import as we go through the examples. And a library like Keras, which is another library that helps us apply some of the deep learning techniques that will come by. So let's import so in this case, we are going to import NumPy library. So that's the first one. Pandas for data manipulation, Matplotlib for data visualization, Seaborn for, again, also statistical data visualization. We also set to ensure that our data frames, we're able to view every detail within our data frame. So in the columns, so we also do that by setting the set option first parameter to display.max column, as well as display max column width. So aside from that, we also show a visualization in the notebook. So let's do that. Actually, we only need one here. We don't need both. But yeah, let's just run that. If you see this pop up, you just need to save a copy in Drive. All right, so once we have done that, we'll go through a classification example where we are going to create a classification deep learning model using, again, neural networks. In this particular classification model, we'll make a prediction on whether a person survived the Titanic disaster. So in this case, we're going to use a Titanic dataset. We have a training dataset and a test dataset. We'll use the train dataset for training and testing, train test dataset for evaluating our accuracy for a model. So yeah, let's go through now the steps that we need to go through. You'll note that we won't exhaustively go through each and every step. We'll just focus majorly on the data modeling section, so don't worry so much about that. So let's import the train dataset and preview the first three examples. Once we have done that, and the first three records, not even the first three records, just a sample of, just a random sample of 3 records from our data set. This just gives us an idea of our data set and the structure of it generally. And we can see that each data set actually represents a person. 0 means they did not survive. They were in this class. This would mean they are male or female. This actually would be, I think this is male. Age and also fair. This is how much they paid. To explore our data, you can just check the individual unique values in the survived column. So we, because this is actually the target variable, 0s and 1, and this is actually what we are trying to predict. 0 would mean they did not survive, 1 they survived. So we check the shape of our data set or the size. We have 891 records and 5 columns, which are the ones that you see here. The next thing that we do is we check the data types for the data set, which you can see here. They're all in the they're all in a good format, but we might want to change this, the age to integer later onwards, because age normally would be an integer, not really a float. But that may not necessarily impact so much of our analysis. For now, we also check for missing data, and we don't have any missing data across all columns. So we select the features. So we are going to select the features that we want. So what we want are our first, so we want to select our features which are class, sex and age, and survived as our target. So that's what we're doing here. Only that in this situation, we're using a different method where we are getting the, we're using a different method for selecting the features, and we save them in X, and then we select our target variable and save it in Y. Then we split our data set using the train test split function, which we pass the X data set, the feature, the Y data set, and then the test size. This will just represent the size of our test data set. How big do we want? We could have actually decided to use what we have here, but in this particular example, we've decided not to, and we've set random state to 0 to be able to have our results be reproducible. So the reason why we set, again, test size to 0 is that we want that 30% of our data set, which we have here, this data set, to just have the test set to be the test set. And the outcome of this are just 4 data sets, which we store them in this particular variables, these 4 of them. So let's run that. And then we create now our base model, our traditional machine learning model, so that we can be able to compare its performance with our artificial neural network based model. So, so in our situation, we import the random forest classifier, we instantiate it, and then later we train the model, and then perform predictions to be able to, we perform our prediction with that particular model, and then we check the metric. So we check how well it performed. And we're just using accuracy score for ease of learning. We could use other metrics as well. Now we decide to now create our deep learning model, and we import the Keras library, which will help us be able to build our deep learning model. And we import these classes, sequential, dense, and dropout, which will be important in our model. So the first thing that we do is to instantiate the artificial neural network by instantiating or creating an object for the classifier, so sequential classifier. And then the next thing, once we have done this, we are going to define our input layer, hidden layer, as well as our output layer. For ease of learning, we'll try as much as we can to make this to be a bit easier to learn. So we have already now instantiated we have already created our object. Then the next thing is to define our input layer. So initially what we are going to do is to use the add method, and inside it we are going to pass different parameters, actually one particular parameter which is dense, and inside dense we will additionally now have different parameters that we can be able to work with. So in our situation here, we set units to 100, which just defines the neurons that we want in our layer. Then we also define the input dimension. These are the number of features that we have, and then we also provide an activation function for that layer. So actually in this situation, we are defining our first layer, and then we also defining the activation function, which it's not only applicable to just the hidden layer, but you could also apply it to the input and the output layer. And we also add something that we might have not mentioned in our reading, which is a dropout regularization function. So the dropout regularization function will just help us to avoid our neural network from overfitting. Overfitting is that it learns, our machine learning model might end up learning so much from the data, such that when we give it new pieces of information, it doesn't it doesn't, if we want to make predictions and those predictions that we and the input that we give it are not closely related to, or not close to the training data that it had learned from, then it might make a big mistake. But to avoid that, we add now what is called a dropout regularization function, which we set here. And we set what is called a dropout rate between, normally you can set this between 20 to 50% or 0.2 to 0.5. And also we just set seed to 2 to just be able to get reproducible results whenever we want to share this work. So that is now our layer, our input layer. Our hidden layer would look like this. This is not second, it's just hidden. So our hidden layer would look almost closely to our input layer, only that in this particular situation, we would define our units as how many neurons that we want within our layer, and then we define the activation function and a dropout regularization function to again prevent our model from overfitting. And lastly, we add an output layer. So we can still add more input layers, more hidden layers, sorry. Another hidden layer and another hidden layer. But for ease of learning, you can just work with the minimum number of layers possible. And then when we realize that our machine learning still hasn't got, our deep learning model, our machine learning model hasn't yet gotten to a point where it has met our metric of success, then we can optimize that by simply determining or changing the number of input or hidden layers that we have. Once we do that, we add an output layer, which we still do the same thing, only that in this case we don't have a dropout function, regularization function. In our situation, we set the number of units as 1. For classification problems where you are trying to predict whether something, or we are trying to predict a 0 or 1 or class, we would normally set as the units to 1, and also set the activation, and set the units to 1. But the activation function, we can use a different activation function, such as a sigmoid function. But generally in our situation here, once we have an input layer, output layer, so just to explain a bit more, when we are working with an output layer, this would just normally be a 1. So 1 would just map values between 0 and 1. So our model will always, if we try to predict something and we give it some input data, it will always give us a 0 or a 1 as the outcome. So let's run that to be able to define our artificial neural network. Then once we have done that, we mentioned that we would need to compile our model, and then later onwards train it. So the next thing would be to compile our model, which would generally involve using the compile method, and inside it, or function inside it, we would have these parameters. There's the optimizer, which just controls what is called a learning rate during training. So it's how fast the optimal weights for the model are calculated. So that is a function that we can be able to define. So we define the optimizer. It's actually not a function, it's an algorithm that we want to use when it comes to calculating now those values for the neurons that we have in our model. Then we define also our loss function, which just defines how closer we get to our loss or the errors that we have within our model. And this can be either binary cross entropy or categorical cross entropy, etc. It just depends with how you want. And what we want here, by the way, this just depends again also on the problem that you have. Like in our situation, we have a classification problem where we want to um, predict two values, zeros and ones. But in a situation for multiple classes, we can use categorical class entropy. And the metric that we want to use to just be able to assess our performance for this model would be accuracy. That's what we set as well. The next thing that we do is now to train our model. We use the train data set, and then we also define what are called epochs. When it comes to artificial neural networks, our training normally occurs over what are called epochs, and each epoch is just split into batches, and it would represent just sets of just rows within your training data set. But well, actually, a batch would represent one or more just set of samples or records that will be considered by the model during training. But an epoch is just a pass. It just represents one particular person. We just call it a pass through the rows within your data set. And we also define the batch size for each and every epoch, how many of those samples we want to consider during the epochs. So do that. And this is now training, and it will take a bit of some time. And the beauty about Colab is that you're not really constrained so much with the resources that you have. You could always just even up the resources that you commit to this training process by going to runtime and changing the run type to either a GPU or a TPU. But if you also want additional ones, you could always consider additional processing power. You could always consider changing that and running that again. But that will significantly reduce the time it takes for the training of your model. So that is done. Then we can then evaluate our model using our test data set as shown. So this, you can see that we have 0.805 as our accuracy metric, which slightly isn't as better. This actually random forest actually works best. Actually looks like it's performed better than the neural network. So what we could do is probably optimize our model, maybe just changing the number of epochs. Instead of 300, we could even decide to put to 500. We could also decide maybe to change the number of layers. So in our situation here, we could add another layer, something like that. Or we might even decide to optimize the number of nodes per layer. So inside the layer, we might even just maybe have this as 200 and also this other one is 200 to be able to do that. Let's do that. We can also do that as well. I'll do that for that, and also for this other case, training our model. 500. Okay, it take a bit of some time. I could even stop this. Let me just stop this. and change the accelerator that we have. Let's just use okay, it will terminate our session. So let's use a GPU save and see what will happen. So it's going to connect to a GPU, which will allow us to just go through the entire process much faster. So again, if you try to click on any other space or place, because our session was terminated, you'll get an error. So that means you just need to again go at the very top and rerun all the cells that you had initially. So I'll just rerun all of them. And the beauty about it is that we will be able to execute or even train our models in a much more quicker way than before. So let's define that and then compile and then train our model. So this should happen much more faster than we initially had. And as you can see, and we are going to 500. So that's on 60, 70, 80. Should take a bit of some time. So I'm just going to have that. And again, the idea here is that we're trying to optimize we're trying to just improve our model by just optimizing the number of epochs, number of layers, nodes per layer. But the idea here is that you sometimes would do this manually to just see what would yield the best outcomes. So initially we had 0.085 when we only had one hidden layer, but in our situation we might want to have another layer. So we might want to add multiple layers, maybe 2, 3, but of course that contributes to just having machine learning or deep learning model that takes time when it comes to training. Then let's check our accuracy to see whether that worked. 0.0897. So if we look at it's actually now it has gotten to this particular point. So we have improved our model to this particular point, which is okay, and we can still further continue optimizing that and also even adding more data, etc. All right. Once we have done that, we can make predictions. So assuming that we had again, we are now answering the problem that we had initially. Want to predict whether a person will survive the Titanic disaster or not. So let's make a prediction. So in our situation, we might want to determine whether a 40-year-old woman in class 4 and they paid paid 30 survived the Titanic. So we can make this prediction by representing this particular piece of data in a NumPy array as shown. And then we would be able to use the predict method to get the predicted probabilities for each class, and then be able to get the predicted class using the argmax function from NumPy as shown. So let's do that. And we can see that we have a 0 as the predicted, which would mean that that woman did not survive. And we can play around with this. Again, there are many factors to consider. You could also study your data set more to just ensure that it's balanced. So you have just as equal number of women as well as men within that data set. Or you could also have, you could also ensure that your target variable, you have as many target variables belonging to one class over the other. So not target, but in your training data set, you could have that target class be 50-50. So 50% of those records in the training data set need to belong to one class, while 50% belong to the other class. So that's it with regards to classification. Work on the challenge. There's a classification challenge. Then when you're done, then we'll go through regression. All right, so the next thing that we are going to go through is a regression example. We'll still use the same approach when it comes to working on the project, where we import, explore, prepare data modeling, and make predictions. Only in this case, we're going to use a different data set. So let's preview this data set. It's a fish data set. It contains weight. So we want to predict the weight of fish given this data set. So this is how the data set looks. We have species weight. This is our variable of interest weight. Length, the length 2, length 3, height, and width. These are our features. Okay, so let's explore the data a bit. We can just display a statistical summary to see whether there were even missing values. We don't have any missing values because all the counts are equal. And we can also have a look at some other statistics, but for now we won't go deeper into that. We can explore our data set to just see whether we have any positive or negative correlations, which we do when we see high values of that, but we can also just of the correlation coefficient, but we can also just use this to just see this is just a heat map to be able to see how our values or data sets variables are correlated. Okay, this might be useful again when you're working with those base models, because those base models tend to have assumptions, something like linear regression. Okay, moving on to data preparation. So we then decide to select our data, then features as well as the target. So we store them in X and Y respectively. Then once we do that, we split our data set, test split. We have X and Y, and the test size, we want it to be 20%. We also want to ensure that the random state, we set the random state parameter to 42 to ensure that our data set is our work is reproducible. So one might be able to create a machine learning model and work with the same test and training data set. Something to note also is that let's not even that. Let's just set that. Oh yeah, I wanted to highlight the fact that we can set any value for random state 0 as well as 42 or any positive value, and that would still work to just ensure that our work is reproducible. Then we move on to data modeling. We create our base model just as we did earlier, but in this case, we'll just use a decision tree regressor. We import the algorithm class, then we create the model, we train our model, and then we make predictions. And then we preview the mean square error, because this is the metric that we are going to use to assess how our model performed. So a value closer to 0 means our model actually made less errors. Again, now we shift to our neural network. We will use the same approach where we import our libraries, which we don't have to because we actually are using the same ones that we had imported in the previous example. Then we instantiate our artificial neural network regressor. Then we still actually use the same class for classification as well as regression. The only thing that will be different will be actually how we define the output layer for both regression and classification. So we instantiate our regressor, we add our input layer. We have 5 input features. That's what we define there. We also define the activation function, number of units. This can also change depending on what you want. We add a hidden layer. The input layer, a hidden layer. It's not second, just a hidden layer. We also define, by the way, we also defined our regularization function, the same case here. Here we also define our hidden layer. We just want one. Then we define our output layer, and we set this to 1 because we don't want to include an activation function because we are working with regression. Normally in such a situation, we would just we wouldn't define any other parameters for that. And the reason is because, again, we are trying to predict a continuous value instead of a classification value. So we define our neural network. We then compile it. We use the optimizer to be able to define the values of the neurons. And we define that we want to use mean absolute error, which essentially would be critical in helping us be able to work with our model. And we also define it there. We train our model over 300 epochs. This should go faster because we are using a GPU. And then we can now use our X test data set to determine the performance of our metrics. Here we are printing out 3, but we can use the last one is actually the root mean square error, which in our case over here it's 259, which is actually really poor than what we had initially for the decision tree regressor. But again, we can add more input layers, so we can decide more hidden layers. So we can decide to add a hidden layer there. Actually, we'll add 4 and then change this to 100, and then remove the input dimension. We don't need that. Oh, we don't need that. I should have copied the one below, but I just used the same one here. Again, we don't need that. We change that to 100. And then we can change the epochs to 500. And let's set this again and compile it, and then train it. Again, the more you have the more you have more layers, the longer it's going to take when it comes to training. But again, with a GPU, it's much faster than before. So it has finished. Then let's rerun this. And actually the root mean square error has gotten up. So it means it's not as we would have tried to do something else with regards to that. But generally, that just tells you a bit more about how your model performed. But in our situation, we could again further optimize how we want with our model. So we could also decide to also explain our model using what is called the SHAP library. So it just helps us to have a summary of our features and the impact on the model output. So let's do that. Let's install our SHAP library. And then once we have done that, we can now create a visualization, a summary plot that gives us an idea of which were the most important features and which were not. We won't go so much into details when it comes to working with the SHAP library. We will just create a summary plot as a bar plot, which is just generally would want. And we would want to have those values, which are called SHAP values, displayed in a plot, which would generally give us an idea of what features contributed the most to the predictability of our model. And you can see length 2, length 1, height, width consecutively contributed most over length 3. Then we make predictions. So you might want to make a prediction. Maybe you wanted to determine the weight of fish with the following dimensions. We represent that in a NumPy array as shown. And then we make our prediction. And we get 176. And generally, that would be it. But as you might have noticed, our regression model based off artificial neural network wasn't the best for this particular case. So we might mm, consider just using the base model in such a situation. Once we have gotten to realize maybe in such a situation we are not suited for using our neural or for using a deep learning model. And this is just a good example of a situation where deep learning machine learning model might not be applicable, especially when you have a small data set where traditional machine learning models tend to outperform um, deep learning models. So yeah, so that's it. Work on the challenges, and once you have done that, verify your solution using the solution notebook that we have given you. And once you do that, then we'll continue to the next steps. All right, so the next steps, once you have gone through the practice work, is to go through now this project, which will help you just put into practice what you have learned. And the idea is that you are going to apply those deep learning concepts for this particular situation. It may not necessarily be that you're going to apply for both cases. It could be, actually, it will be one particular use case, whether it's classification or regression. Then once you've done that, you can use the solution notebook that you provided for the project. Also keep in mind that we've also provided a guiding notebook within this particular brief document. Use that brief document to guiding notebook that we've provided a link to just help you go through now the project with ease. And that's generally it with regards to this particular course. The next thing that I would recommend is that you work on different kinds of application, or you get to learn more about how you can be able to use now deep learning models for when you're working with text data, just to be able to learn also applications of such. And also you could also go through a course also on optimizing your deep learning models with again, optimizing deep learning models, just different techniques of how you're able to do that. We covered a few, but you could always just spend a bit more time on that. That's it. All the best in your learning journey, and hopefully we'll be able to interact in a future course. And all the best in your journey. Bye bye.